Hello guys, today we can talk about radioactive decay. In last lecture we talked about nuclear forces, the forces that we usually found inside the nucleus between those particles, those nucleons, right? Those protons and the neutrons. And we talked about strong and the weak nuclear forces. Once there is a force involved there, that means there might be attraction or repulsion, right? And that you need to be aware of. But in the case of nuclear force, if there is a strong nuclear force, then that is a attraction going on there, right? There is a attraction going on between those nucleons. But let's say if the nucleus becomes unstable or it's under, let's say, the weak nuclear force, then what's going to happen? That nucleus or those nucleons going to go through a decay process called the radioactive decay. And here are the list of the terms we will encounter during our discussion here: the parent, daughter, particle, decay, and radiation. Here, as you can see in the picture, you have the parent nuclei, where you have protons and you have neutrons. Once this nuclei becomes unstable or very excited, it has to go through the stable conformation, right? So during that process, what's going to happen is you're going to release the energy here, right? And you're going to get some kind of particle here, right here, okay? And that is, my friend, radioactive decay. Okay, when the unstable nuclei goes through this process, right, it's going to give you a particle or a radiation, and it's going to give you a daughter nuclei because the parent nuclei is big, so the daughter nuclei will be smaller than the parent nuclei because it's going to lose this particle. Okay, but remember, it's not always the case, right? The parent nuclei are going to become the daughter nuclei, and the size will change. I'm not saying that. There is a few exceptions you'll note in few seconds. In the case of gamma ray decay, the identity not going to change. Okay, in the case of gamma ray, we'll talk about that. But for now, what you need to know is the parent is undergoing radioactive decay. Okay, you're giving radiation and you have a particle. Okay, that's pretty important. Okay, so there are mainly three types of decay, and we need to understand how the decay process works in these three types of scenario. The first one is called alpha decay, and second one is called beta decay, right? And the third one is called gamma decay. In this case, the X and the Y represents the element. Okay, if it goes from X to X, that means the identity not going to change. The element is same. If it goes from X to Y, then the element got changed. For example, if it is going through carbon to carbon, right, then that means the element didn't change, right? Something different happened. Okay, if it is going through carbon to nitrogen, or it can go through carbon to boron, let's say, right? Now, let's say this is X, then this is Y, right? So there is a change in the element identity, and that's very important. You need to look at for this one. Okay, does the identity change? Okay, so look at this first case. There's the alpha decay. You have X going to Y. That means the element got changed, right? The identity got changed. And here G is the atomic number, and the atomic number is the number of protons. And the A is called mass number, and it is the combination of proton and the neutron. And we know that, right? We already talked about this one. In the case of alpha decay, what's going to happen is you have to subtract mass number here. Look at you have to subtract by 4. Okay, and you also have to subtract the atomic number by 2. Okay, that basically means you are putting 4 here and 2 here in the case of alpha decay, right? And the alpha is a particle, right? So here you put 4 on top and 2 on bottom, because you subtracted that. Whatever you subtract, you have to give that to the particle, that alpha particle. We need to know about conservation of energy, right? You cannot just give up something and it's just going to disappear. No, that's not going to happen in nature, right? So if you subtract 4, you give 4 to the alpha particle. If you subtract 2, you give 2 to the alpha particle, right? In the case of beta decay, though, there are two types of beta decay we'll talk about. One is called beta plus decay and another is beta minus decay. But how are you going to know it, though? Okay, before I'll explain that beta plus and beta minus decay, let's see what's going to happen to the identity of the element. Here you have a x and you're going to y. That means identity of the element changed, like this case, right? What about the a, the mass number? It didn't change. Okay, what about the g, the atomic number? Oh, you added 1 on the g. Okay, so in the third case though, here the a is same also, g, but you subtracted g here. If you add 1 on g, right, and if you subtract 1 from the g, you get this beta decay. But the mass number not going to change. Remember, if you add something on g, you have to give this b negative sign. That's called beta minus decay. If you subtract from g, then you have to add the positive sign here, right? And that is called beta plus decay. That's how you distinguish them. Okay, that's very important. The last one is called gamma decay. What you see is the X going through the decay process and giving the daughter nuclei X. That means the element identity didn't change. That means the G remained same, because the proton gives the identity for element according to the periodic table, right? What about A, the mass number? It didn't change. It's the same thing. But what happened here? Look at here. This is excited nuclei. Look at this. This thing gonna show you. This is, let's say, the symbol. Let's say, okay, this is excited version of X, unstable one. Let's say, and it's going through that decay process, and now it is stable and it's happy now. Okay, is it gonna give you a particle? No, because you did not change any number. You didn't change any mass number. You didn't change any atomic number. How are you gonna give the particle? But what you can give is a gamma ray, and the gamma is not a particle, it's a ray. Okay, that's very important thing to note. Okay, this is pretty much whatever we talked about. Okay, this is same thing. Okay, here is the alpha decay, and there's a beta decay and the gamma decay, and this is, I already talked about that. In the case of alpha decay, you subtract, look here you have a minus 4, you do that, mass number minus 4, and you do atomic number minus 2, and whatever you subtract, you just give that to the alpha particle, and you're going through parent to the daughter, and you're giving that alpha particle, and the alpha particle are double positive charge particle. Okay, that's important thing to note. Okay, in the case of beta decay, here we're talking about what kind of decay. Say there are two types of beta decay. Look at this and say, just tell me what kind of decay is this. This is a beta minus decay, because the beta has -1 on it. If you have -1 on it, that means you're adding 1 on the atomic number. That's what we talked. And here you got the beta particle. In the case of gamma emission though, okay, you did not get anything. The gamma did not get anything because it's just a ray. It's not a particle. And you are going through excited nuclear state of X to the stable version of that daughter nuclei, and it got just relaxed. Think about this. You do a lot of work in type of thing, right? You are very, very excited, and you kind of, and you just kind of like so much going on in your life type of thing, right? You want to relax, because, and that's the process of decay. I don't know, that analogy might not work well, but yeah, the idea is you are excited, you want to go to some kind of relaxation process, and give some kind of ray, but you're not going to give any particle here. And that's pretty important concept here. Okay, right here. Okay, so this is just showing you, like, if there is initial amount of this nuclei, if it undergoes this decay process, you get the final amount. Look at the inside this nuclei, the particle, those nucleons, the number getting low and low, right, over time, right? Here initially you had 100% radioactive isotope remaining because nothing got decayed. This is a parent here, right? This is a parent and this is a daughter. Okay, so if it goes through radioactive decay, and let's say, okay, the time in which half of the original number of nuclei, in this case 100, right, decay, number of nuclei decay to the to its half. Let's say you're going from 100 to 50, that's half, right? And if you, the time that it takes for that thing to happen, going from 100 to 50, that time is called the half-life. Basically, the half-life is the time in which half of the original number of nuclei decay, and that's pretty important. And that's it, and I'm not going to tell you more than that. But remember, the rate will be different for different element, okay, or different isotope. Let's say the radioactive decay process will be different, okay, for different isotope. And again, here you can get radiation and you will get some kind of particle. And the particle, in the case of gamma radiation, right, gamma is not a particle, and if there's a gamma decay, you don't get any particle, you get radiation. That's pretty important concept right there. Okay, let's practice here, and this is pretty important here. So, and the concept is, if this is the alpha decay, right, if it is alpha, what do you have to do? A minus 4, G minus 2. That's very important. Okay, if it is a beta decay, the A will remain same, but what you have to do, G, you have to maybe add or you have to subtract it. Okay, in the case of gamma, nothing will change, pretty much everything remains same. Okay, but you release that gamma radiation. Here in the first case, you're going through uranium 92 and 235, and you're going to TH here, right? And remember, you're going to 235 to 231. What's the difference? If you subtract 4, what's going to happen? 231, right? Here, if you subtract 2, what's going to happen? 90. That means the C is a alpha, and it's going to give 4 and 2. That's pretty good, right? Okay, okay, second example. So it's the same thing, uranium, right? So you have a 235 and 92, but we don't know the element now. Okay, does the element gonna change? Yes, because it is a beta decay. We know this one, right? But look, it is a beta minus decay. That means whatever gonna come here, okay, whatever gonna come here, what do you have to do? Okay, whatever the element gonna be there, you have to do something interesting here. What are you gonna do? Okay, what is the element? Okay, the element gonna be NP. What is NP? You should know it. It's called neptunium, right? Neptunium. So that means you have to add G plus 1, right? So what does that mean? 92 plus 1 gonna give you 93. So 93 is the neptunium, and the 235 will remain same according to here. Okay, the A remains same. Okay, so the third one, what are you going through? 11 to the 11. Does A change? No. What about the G? 6 to 5. It does change. So that means you are subtracting 1. 6 minus 1 gives you 5. That means the G value got changed. That means it should be the beta decay. Is it going to be positive or negative? Because you subtracted here, that means it should be positive. Okay, it should be positive. And that's pretty important concept. Okay, the final one is you are going through 60 and you are going to 60. You're going 27 to 27. Oh, no change on A, no change on G, but it might go through this excited nuclear state to this let's say the stable nuclei, right? and nothing changed on A and G, that means it has to release gamma ray. Okay, right here, gamma ray, no change on A, no change on G, and that's pretty important concept. Okay, this is our decay series. Sometimes you will encounter this type of question, but just it's pretty simple. You just need to know what you're doing. So you're going through 223 to 219. It's just the difference of 4, right? And you're going through 88 to 86, so difference of 2. So that means it should be alpha decay, right? 219 to 215, 86 to 84, again this should be alpha decay. If you're going from 215 to 211, there is a difference of what? 4, difference of 2, so it's again the alpha decay. If you're going through the PB 82 and 211 to the BI 211 and 83, the 211 is same, so that means it should not be the alpha decay, right? But what changed is the G, so you added on this, right? You added on it, so that means it should be beta minus decay. Okay, if you're going through BI, there's a two sides it's going to go through, right? BI to PO, right? So what happened? 211 not going to change, 83 just changed. Look, 83 to 84 you added, so that means the particle you're going to get is subtracted on, beta minus decay. Okay, so what about here? You're going through 211 to 207, and you're going through 83 to 81, so it should be what? There's a difference of what? A minus 4 and G minus 2, right? So that means it should be alpha decay. Okay, the finally here, so okay, so can you predict from this side? No, because we don't know what kind of decay here, and we don't know the final product, so we cannot predict this from this side, but we can predict answer from this side. Okay, so if you have a PO and if it goes through alpha decay, we know that. Okay, if it goes through alpha decay, we have to subtract 4 and from the 211, and we have to subtract 2 from 84, so that means it's gonna be something like 82, and the top value gonna be 207. And look at the periodic table, the 82 value gonna go for PB, so that's the alpha decay gonna give you this result. That means we have to predict here right now. So you're going through 207 to 207, no change on A. You're going through 81 to 82, you are adding 1 to that G value. That means it should be beta minus decay. Okay, that's pretty much it. Okay, so you have to just work through it. It's pretty simple, and you can solve any kind of questions that you will encounter in the MCAT. Thank you so much for watching. Bye bye.